In case, say, for this example, we don't have a sufficient allowable bearing capacity or soil bearing capacity to resist the imposed load on the foundation without a proper factor of safety. While for the piling foundation system, we have an over-designed case where the capacity of the system is much higher than what we need. But if we consider to reduce the number of the piles and use the raft foundation load sharing in our system, we will be something in between, like the curve B. Since when dealing with the finite element and the practical aspects of the foundation engineering system, we know that most of the cases we received reports with basic information, the soil report with basic information like SPT, the standard penetration testing, or the CPT, the cone penetration testing. And you will develop the parameters of your model initially in codes, from those parameters, from the SPT or CPT and the like. But it is crucial important to know the limitations of those methodologies and the correlations you are using. And for example, I'm bringing a very important terminology that being overcome usually by most of the engineers and even in most of the soil reports, which is the hammer energy correction for the SPT. For example, if you have two rigs, one rig with an SPT hammer energy efficiency of 40%, which is the blue one, the blue line, and another rig with hammer energy efficiency of 80%, which is the black one, the black line, okay? If you have both of those machines went to a site, to the same site, and they conduct the standard penetration testing in the same soil, they will end up with different profiles. The blue one, for the same soil, the blue one, which is the 40% hammer energy efficiency, will end with this profile, and the black one, which is with 80% hammer energy, will end with the black line. If you design your foundation system on the case of 40% without a correction factor, and actually you are getting this difference because you are assuming that the hammer energy correction factor as 1, or you are assuming that the energy certificate, the energy efficiency equal to 60%, which is not the case. It might be 40, it might 80%, it might be any values. So you have to measure it, or you have to ask for it at least. If you have designed a foundation system on the blue line, which is the 40%, you will be in danger and you are overestimating the bearing capacity of your system. While if you design on the black line, which is the 80%, you will be over designing and your design of the foundation will not be economical. However, if you use the exact correction factor using the actual energy efficiency for both of them will yield the same results, which is the red line, which we call it as N60. So this is a very minor detail you have to pay attention, and it can control your complicated finite element analysis. So it is a rubbish in, rubbish out. Another aspect is the plate load test. Usually, the plate load tests are used to verify the bearing capacity or the modulus of subgrade reaction of the foundations using the analytical solutions, for example, in Joseph Bowles. However, this test is very useful for us if properly used, but most of the cases, or in a lot of cases, it has been misused, unfortunately. For example, the analytical solutions or analytical equations you are using is limited to what we call as half elastic solution. Means the soil is homogeneous and infinitely extend to a larger depth. But usually this is not the case, and you have a certain limitations in layered soil. If you have a layered soil, then the use of this plate load test in the design is not as straightforward. Another aspect is if you have the size of the footing, the size of the foundation system, or the width of the foundation system you are using in the site, for example, is greater than 6 to 15 times the width of the plate bearing size you are using, then this is not a straightforward application for the plate load test. The Prototype analytical solutions provided in the books or the codes or in the manuals are not applicable for certain cases. If your width or size of the foundation is 6 to 15 times more than the foundation system, even if you have a homogeneous soil, is not applicable to be used directly. Again, as we said, the plate load test is limited in layered soil, and the analytical solutions cannot be used even if your foundation size is less than the provided limitation. However, can we still use the plate load test? Of course, we can use it when a special considerations is being given to the results and the conditions of the plate load test. For example, we usually use the plate load test to calibrate the upper part of the soil or the top part of the soil. If you can see, the blue line represents the field results or the test measurements from the field for the plate load test, and then we have back calculated using the finite element modeling using Plaxis 3D, and we yield almost to the same behavior, and that's how we say now we have a calibrated model, at least for the upper part of the soil. For the deeper part, you can use a pile foundation or laboratory testing like triaxials or consolidation tests. And another aspect of and important one actually is the modulus of subgrade reaction, because most of the structural designers depend on this modulus of subgrade reaction, and sadly some of them are taking it directly from the soil reports, which is usually equal to 120 times the allowable bearing capacity and the metric units. This is not relevant at all. You remember when we talk about the averaging technique and it might be fatal? Well, most of the cases at their best, the soil reports usually, especially in this region, depends on averaging technique, and they are not project relevant. They will assume a soil bearing capacity required, they taken from the structural designers, and they don't consider the actual shape of the foundation, the actual load distributions, the actual column spans will make the KS or the modulus of subgrade reaction or the areas spring or provided in the soil report not relevant to be used in the structural design. So pay attention to this aspect. Do not use the modulus of subgrade reaction or the area spring provided in the soil report directly without a geotechnical design engineer translates it to it or change it or twist it or recalculate it to a relevant value to your case. Why is that? Because the modulus of subgrade reaction is not a constant and is not an intrinsic property of the soil. It depends, just as the soil bearing capacity and the settlement, it depends on the type and the layer of the soils. It depends on the type of loading, the magnitude of the loading, the center of gravity of the loads and the center of gravity of the foundation, the geometry of the foundations, the groundwater tip, the groundwater table, the depth of foundation, and so on. So it is not a constant value. For a same foundation system, if you change the magnitude of loads, you will have a different KS or different modulus of subgrade reaction. For the same type of soil, if you change the size of the foundation, we will end up with a different value of the KS. So no, it is not a constant, and it is not a single value as well. Both the settlement, SPC, and KS is not a single value. It depends on the constraint level, it depends on many aspects as well. And also another important aspect, but before talking to the last point, I will show you this diagram, what we mean that KS or the modulus of subgrade reaction is not a constant and not a single value. For example, this is a post-processing or output results from the finite element analysis conducted in Plaxis 3D for a raft foundation system. We get what statistically we know as histogram. So what is the histogram? Actually, it is the frequency of the repetition of the values beneath the raft. For the modulus of subgrade reaction, you can see that the most predominant value is 3 kilopascal per millimeter, for example. But again, the averaging system or concluding that directly I will adopt 3 is not healthy always. So what you can some people might use weighted average technique, some people might use iterative modulus of subgrade reaction coupled with or connected or exported to the structural design, and with some iterations both of the models will converge, and some people will simply do a coupling between both the models. However, in certain cases the modulus of subgrade reactions has no physical meaning. It will simply act as fitting parameters. If you are familiar with regression analysis and statistical analysis, we have something called fitting parameter. In certain cases, the modulus of subgrade reaction, or the Ks, will act only as a fitting parameter, and that it has zero physical meaning. In those cases, like the uplift, the consolidation or swelling of the soils, the long term, the short term, you have different values of the Ks and different histograms. So you might analyze case by case in according with or with coordination with the structural engineers or the structural designers. And there is probability, there is upper value and lower values, upper limit and lower limits. And also, and if you consider the coupled analysis, it's not the end of the story, because most of the coupled analysis usually depend on the last phase, and we know that the finite element analysis is being conducted in staged construction methodologies. So usually in the coupled analysis, most of the tools are based on the last phase, which is the last or the final Ks value. So the values in between you have to manipulate and you have to analyze and post-process before concluding the design. Another aspect of the design that the piling, the skin friction of the piles is not linearly increased with the depth, as well as the SPT, as well as the soil bearing capacity, as well as the stiffness. So it is not a fixed rule that the skin friction or the soil stiffness or the soil strength is increased or is increasing with the depth. For example, you are seeing here some increment in the depth and reduction, so it's not a constant and not linear. Another important aspect as well to consider in the piling foundation system is the buckling. Usually, most of the piles do not buckle or are not subjected to buckling. And the engineers will think straight away in columns when we talk about buckling, or beams, or steel columns or concrete columns. However, when you are dealing with small diameter piles or micro piles, you have to check the buckling mechanism. And there are certain guidelines in the codes and in the manuals to help you doing so. Again, for the piling foundation system, you can conduct the pile load test on site and use it, as we said, to calibrate the model. You will get the bearing capacity of the piles from the pile load test. You will get the settlement, and as we said, you will monitor the creep settlement or the creep behavior of the piles, and you have to determine whether it is acceptable or not. And finally, you will use it to calibrate the finite element modeling. And you, with this pile load test, you might get advantage of using the embedded beams element in the finite element modeling rather than the volume elements, because you can estimate the end bearing capacity and the skin frictional capacity of the piles, which is an input for the embedded beams elements. Well, some of the engineers think that if pile foundations are extended up to the rock foundation, then it will not settle. And unfortunately, this absolutely not realistic and not true. And it might be interesting to go and see this case study, which is recently happened in September 2020. Let me share it to you. The pile design error leads to demolition of Sheffield building in UK, and it is a major project in the UK, and they found that the pile foundation does settle, and it was in excess of what expected in the design, so they have decided to demolish all the building and repile the whole site again and build it again, which is a huge cost for the project and delay as well. It will cost them another 18 months of construction. So you have to pay attention. Another aspect when dealing with the finite element modeling is the soil constitutive model and what type of soil constitutive model to use in the finite element and how to use it and how to calibrate its parameters. This is crucial aspects you have to consider. Another important note also the boundary conditions. We know that the finite element modeling is a boundary conditions dependent and we don't want our results to be affected by the boundary conditions. Usually in the structural modeling softwares, you don't have to consider or to enlarge the model beyond your raft or your structural geometry. But in the geotechnical or the soil model or the soil finite element model, you have to extend your model well beyond your raft foundation or your foundation system in the three directions, X, Y, and Z, in a way that not affecting your results. And this will depend, the amount of this enlargement will depend on the soil constitutive model you are using. As a good and quick guideline, you can refer to this table. For example, you have a Moha column, which is a special case of a Drucker-Breger. You have the CAB model and you have modified camp clay. And finally, you have the hardening soil model and the hardening soil model with small strain stiffness. If you can say most of constitutive soil model is the hardening soil model and the hardening soil small strain stiffness model. Why is that? Because it is applicable almost to all type of soils. However, there are certain problems or certain geotechnical challenges. You cannot use this, at least not alone. If you have a liquefaction or if you have a creep, or if you have cyclic loads, you have to consider another constitutive model. But generally or mostly in foundation system problem, especially on sand or clay or silt, you can use the hardening soil model or the hardening soil with small strain stiffness. For those who are familiar with hardening soil model, just to know how important to develop a sense for what the soil constitutive model parameters means. We have something in the hardening soil model called the power factor, M, which called M, okay? If you have an M of 0, you will end up with a constant stiffness of the soil with the depth, which is here reflected as the stress. If you, and this case reflects the case of pure rock material. And if you have an M value of 1, you will end with a linear increment of the stiffness, and this represents a clay material. And if you have 0.5, you have a pure sand material. So you have to develop a sense what each parameters means before using the finite element modeling. Another crucial factor or crucial aspect when dealing with the safety analysis and the finite element, one of the most advantage or the more crucial point about the finite element modeling is you can get the factor of safety from the finite element analysis. Okay, but you have to consider the elastoplastic materials of all the structural elements involved. For this, for an example, I'm bringing here this chart for a shoring system where we have a sheet pile, ground anchors, which consist of the free length and the fixed length, the grout body, and the weir beams, and the soil as well. We have constructed this model in the Plaxis, which is a finite element modeling software, and then we have run the SSR, or the shear strength reduction, which is a safety factor analysis tool, and the Plaxis to get the factor of safety, which is the blue line. If you can see the blue line. In this blue line, we get a factor of safety of 2, and only the soil was modeled as elastoplastic material, and the rest of the material was there in the model, but modeled as linear elastic. However, if you consider the elastoplastic properties for all the structural elements involved in the system, you will end up with a lower factor of safety, almost 1.4. So make sure that you are not over designing or overestimating, sorry, the factor of safety. We know also, or you should know, that the finite element modeling is a mesh sensitive, and the results will depend on the mesh properties. And it is always of good practice to conduct mesh sensitivity analysis and to monitor your results. Your results depend. For example, in this chart, I'm focusing on the settlement or the deformation, the vertical deformation in millimeters, and I'm correlating it with the number of elements. And if you can see, at almost 70,000 elements, approximately my line gets yield. So at 120,000 elements, you have the most accurate results, and at 60,000 approximately, you have the worst or the least accurate results. So when to use which again? Actually, if you use the 120,000 elements, which is very fine mesh, then it means that you will have an accurate results, but the calculation time will be so huge, and it is a time-consuming calculation. While if you have a 60,000 elements, your calculation time will be very fast, but it will not be inaccurate. So you have to decide an acceptable level you can accommodate in your project. For example, 70 or 80,000 elements might be okay. It is also of good practice to use the parametric study or optimization of the system before concluding the foundation design. For example, in this chart, you are seeing the area ratio, which is the area of the piles over the area of the raft foundation in a combined piled raft foundation system. This means the number of the piles. So in the x-axis, as you move positive, you will increase the number of the piles, and the actual load sharing obtained from analysis, which is a result output, not an input. So you will see the differences in the behavior while increasing the pile numbers or the number of the piles, and how the piles attracting more and more loads compared to the low number of the piles. Similarly, you have different number of the piles. Those three colors represents the least number, more number of piles, and the maximum number of the piles. And this is the settlement improvement factor, okay, which is the settlement improved from your raft foundation case in the piled raft foundation system. And you have different length of the piles. If we rearrange this chart into the following chart, you can see clearly the limits of the number of the piles. So this is the number of the piles, and this is the different length of the piles. At a certain point, you will end up with the maximum or the optimum number of piles, which is beyond this point, you will have no significant improvement in the settlement anymore. So that should be considered as your optimum number of pile foundation system. So it's not a straightforward design, it's a trial and errors, it is iterative, and it requires optimization, engineering judgment, and experience to come up with the right amount of piles and the configuration of the piling system and the piled raft foundation. Now we will move to the case study where we have a micropiled post-tension raft foundation system. And this is one of the very recent development in the foundation system, or in the combined piled raft foundation system. It is a new trend, actually, and it has been used by, we have conducted a couple of micropiled post-tension drafts recently. So this project is located in artificial or man-made island, and it consists of 3 towers. Each tower has 465 square meter, and they have a lot of underground pipelines or buried pipelines where they cannot induce a certain amount of stresses, or they have to limit the stresses from the raft foundation system to a certain limit, and they cannot use poured pile foundation because it will disturb the ground, and it will affect the pipelines or the buried pipelines. Therefore, we have proposed something called the micropiled post-tension raft foundation, and this is one of the advantages of the micropiles. It has almost zero disturbance of the system or of the buried surfaces, if properly considered. So we have designed the raft foundation to be a cantilever in the portion near the pipelines, which means it is not supported on the soils, and we have micropiled the supported raft foundation and the other location. And we will have, in the CBRF cases, we will have something in between case 1 and case 3, which is the settlement reducer piles and piles to resist the lateral loads and moments. We have then conducted a coupled geotechnical structural analysis. We have used the soil reports to estimate the initial design, and then we have calibrated the geotechnical model with the pile load test, the plate load test, and we have exported the different parameters to the structural analysis. We couple it with the structural design, and both of the models converge to the same results, and then we have constructed, and it is 100% operational now. Again, we have used calibrated, as you should do always, calibrated finite element modeling for the soil structure interaction analysis. The raft was 1 meter thick, almost on average, and we have 24 numbers of micropiles with diameter of 250 millimeter varying in length. And this varying in length, we determined it based on optimization study. The overall results was, or the conclusion was, we have a cost saving in that project up to 30%, and we have a 50% of time saving. The micropiles installation are very fast, as well as the post-tensioning in the raft foundation helped us to finish the concrete pouring of the raft foundation very fast, and it helped to reduce the reinforcement amount required for the raft foundation. This is a general layout of the project, where you have the unsupported part, 1.8 meter almost, and we have the micropiles distributed only where needed, and this is the supported part of the raft foundation. This is the pile load test, or the micropile load test we have used on the site, or we have conducted on the site, and we have used it to calibrate the finite element model. And this is the worst case scenario in the worst phase results. The deformation is barely 32 millimeter, and the safety analysis was conducted, and the safety factor was in excess of 3 almost for the whole system, the safety factor of the whole system. And this, for example, you can see the areas, the point spring or the stiffness of the piles exported to be verified by the consultants, because usually they cannot use the coupling between the geotechnical and the structural model. So instead we are providing them with the stiffness of the piles, and this based on the worst case stiffness values. In the structural model, you will see that the soil are represented as springs, which is the Winkler springs, or some sort or developed version of Winkler springs, and the piles as point springs. This is the soil as area springs and the piles as point springs. Now, as a career path for freshers engineer and the civil engineering students, we have seen this in the beginning of the session, and you can fit yourself if you want to be involved in foundation engineering. You can fit yourself anywhere in this loop. You can be an engineer, owner representative engineer. You can be a geotechnical investigation or site investigation engineer. You can be a structural design, geotechnical design engineers, or in the construction as a site engineer or safety and so on. However, if you want to proceed with the design part of foundation engineering, you have to develop a certain skills, both soft skills and hard skills. Regarding the soft skills, you have to develop numerical analysis skills, dealing with different softwares and different numerical tools. This is a list of some of those tools. And you have to be familiar with other methodologies than not only finite element modeling, but like limit equilibrium, material point method, as we have stated earlier. And you have to know the limitations of each part or of each tool of your softwares. For example, we know that the soil are discrete in nature and granulars, while in the finite element, we assume that the soil is continuum. So this is not a valid 100% true, and you might consider to use a discrete element modeling for certain cases. But for the foundation, usually we are using, so far or till now, we are using the finite element modeling or the finite element analysis. Another of general softwares and general skills you have to develop with the time to be a competent foundation engineer in your career, in your future career. The lab and field testing, also you have to be familiar with each lab and field testing procedures and what you can get from them, and if you need a certain parameters for your constitutive model, what lab testing you have to consider, or what lab or what field testing you have to conduct to calibrate your finite element modeling, for example. And also nowadays the programming skills are crucial to some extent for foundation engineers to develop and simplify the efforts in designing the foundation using finite element or numerical analysis. And as a last hint, keep updated in your field. Read and read and read again till you become an expert in the subject, and keep updated, because the geotechnical field is very dynamic and there's almost every day there is a new findings in the field. And books are okay, but my advice to you as a cheating, just be updated at least with the research articles, because they are very fast to be read and they are accessible, and you can like involve in some of the research and write your own articles. A good source for that is Google Scholar, ResearchGate. You can keep tuned with those sites or those repository for the final and recent research article or case studies.